Good evening, dear ladies and gentlemen. My name is Altay Zhakatayev, and today I'm defending my PhD thesis. The title of the thesis is Optimal Design and Control of Variable Impedance Actuated Robots. My supervisor is Professor Atakan Varol from the Department of Robotics, School of Engineering and Digital Sciences. My co-supervisor is Professor Matteo Rubagotti, also from the Department of Robotics. My external supervisor is Professor Frank Sapp, from the Mechatronics and Robotics Research Lab, University of Massachusetts, Amherst, United States of America. Today we have as a co-chair internal examiner Professor Luis Rojas Solorzano from the Department of Mechanical and Aerospace Engineering. As internal examiner we have Professor Siamak Fazli from the Department of Computer Science, and as external examiner we have Professor Erdal Kayachan from the Department of Electrical and Computer Engineering, Aarhus University, Denmark. The following colleagues and team members helped me to conduct research. Sultan Rahim, who is currently studying for his master's degree at Nazarbayev University, Ojas Adiatov, who is now doing his PhD at the University of Waterloo, Canada, and Almusan Baymashев, who is currently doing his PhD at the Vanderbilt University, United States. So on this slide, you can see the publications related to this research. We have 4 journal publications and 3 conference publications. So this is the outline of today's presentation. First, I will talk about the mechanical impedance, and I'll talk about different robot design paradigms. Then I'll talk about the hypothesis. And after that, we'll go over the different approaches to control variable stiffness actuated robots. Then we'll discuss, I will talk about different tasks that we performed or implemented using our control approach. And then finally, we'll conclude. So, what is impedance? Impedance in general describes how a given system reacts to external influence or input. In other words, it describes how a given system kind of responds to external stimulus. Okay, so impedance, we can say that it resembles the sinusoidal transfer function definition. Okay, so for example, it's similar to the ratio of Laplace transform output to Laplace transform input. Okay, and for example, if we talk about mechanical systems, then as input we might have a force. As output, we might have, for example, velocity and displacement. So if we focus on mechanical systems, then we have to define the mechanical impedance. So let's imagine we have a mechanical system, then we apply a sinusoidal or harmonic external driving force input force, okay? And then as a response from the system, we get a certain sinusoidal or oscillatory displacement, okay? Steady-state displacement. Then we can define as mechanical impedance the ratio of this driving force to the resultant steady-state displacement. In general, this mechanical impedance is a complex number, and the amplitude of this complex number is equal to the ratio of amplitudes of the force to displacement. Okay, while the phase of this complex number is equal to phase difference between input force and the resultant output steady-state displacement. The real part of this mechanical impedance is called resistance, and it usually describes the rate of energy absorption, while the imaginary part of this complex number is called reactance and commonly describes the energy storage capability. So, given arbitrary or a general mechanical system, the mechanical impedance is defined by the properties of inertia, stiffness, and damping of the system. In other words, the inertia, stiffness, and damping properties of the given mechanical system, they together, combined, they define the mechanical impedance of the system. We know that inertia in general describes the resistance to acceleration, or kind of characterizes resistance to acceleration. Damping describes resistance to velocity, and stiffness describes resistance to displacement. If for a given mechanical system we can vary any of the 3 properties of the system. In other words, if we can vary inertia and or stiffness and or damping of the system, then essentially we can vary the mechanical impedance of the system. So in other words, mechanical systems with variable mechanical impedance are systems in which any of the three properties of the system can be varied. And currently, the variable impedance actuated robots are robots in which we can alter or vary the mechanical impedance of the joints of the robot. Currently, we have all sorts of robots. For example, we have industrial robots, then we have mobile robots, we have flying robots, snake types of robots. So we have all sorts of robots. One of the important goals of the robotics field is to design such a robot which would move with the same agility, mobility, and dexterity as humans and animals move. And one way to achieve this goal is through so-called variable impedance actuated robots or variable impedance actuated joints. Example of variable impedance behavior include, for example, the explosive motions like running, jumping, or throwing, and the slow, elegant motions like smooth touching, texture sensing, and so on. So roughly, we can divide robots into three different generations or categories. Robots of the first generation, they're so-called position control robots. Okay, so for example, TX90 is one example of this case. Then, as the second generation robots, we have so-called active torque controlled robots. For example, KUKA lightweight robot is one example of that. And then, as the third generation robots, we have so-called variable impedance actuated robots. So, DLR arm is one example of this robot. On this slide, you can see the video of the state-of-the-art position controlled robot motion, or kind of example of that robot. So, you can see that in this video, a robot moves very precisely, and you can control its the position velocity very precisely, and this just shows the state of the art, what position control robots can perform. On this slide, we summarize the information about position control robots, or so-called stiff joint robots. Okay, so the main disadvantages of robots are the following: they are not safe, and they are not energy efficient. In other words, they spend energy in all parts of the motion trajectory. They are not compliant, so that means they can't vary the mechanical properties depending on the task that they can perform, and they can't perform explosive motions. While the position control robots, they have the following advantages: they have high position accuracy, they have high bandwidth, which means that they can follow sinusoidal signals with high frequency, and they are easy to design and control, relatively easy to design and control. Here you can see the schematic of the rigid or position control robots. So in these robots, the actuator is directly connected to the link through the rigid connection. So on this slide, you can see the video of the active torque control robot, and what it can perform and what are its advantages. Okay, so you can see that on this video, when this robot hits, for example, an external object, like for example a person, then it stops its motion, so it's safe. This slide summarizes the main advantages and disadvantages of the active torque controlled robots. These robots are also called active variable impedance actuated robots because the variable impedance behavior is achieved by active means, by actively controlling the force and torque. through the force and torque sensors. Okay? So these robots have the following disadvantages still. They are not energy efficient, they can't perform explosive motion, and they also can be unstable. So the advanced controls that are usually employed in these robots, they can become unstable at certain rare conditions. Okay, but these robots have the following advantages. They are now safe, they are compliant. So in other words, you can program them to behave with any desired apparent mechanical impedance, and they have still high position accuracy and high bandwidth. So here this diagram kind of summarizes schematics of these robots. So in these robots you have still the rigid connection between actuator and the link, but now there are many sensors. For example, acceleration sensors, torque, force sensor incorporated into the actuator and link, so that using the information from the sensors, we can, for example, detect when collision happens, and we can modify the robot motion according to that. This slide contains a video where essentially we can see the advantages and the unique features of the variable impedance or variable stiffness actuated robots. For example, you can see that when the robot is hit by a bat, then essentially there is no damage to the robot. Here we summarize the information about the variable impedance actuated robots. So these robots are also called passive variable impedance actuated robots, because here the variable impedance behavior is not something which is achieved by active means, or a variable impedance behavior is not achieved by imposing that behavior. It's variable impedance behavior is kind of intrinsic property of the joint or the robot, and so it's kind of passive variable impedance behavior. Okay, so these robots, they have the following disadvantages. They have now limited position accuracy, they have limited bandwidth, and it's difficult to design and control them because you have more elements in the robots. While the advantages of these robots include safety, energy efficiency, because they can store energy at one cycle of the motion and release it at other parts of the motion. They are compliant, and they can now perform explosive motion. Okay. So here you can see the schematic diagram of the variable impedance joints or robots. So in these robots, the actuator is decoupled from the link. So in other words, it's not directly connected to the link, but its actuator is decoupled from the link. So so-called variable stiffness and or variable damping elements. So essentially, by varying the stiffness and damping properties of these elements, we can change or vary the mechanical impedance of the joint or of the robot. So again, passive variable impedance joints, the variable impedance behavior is something which is intrinsic to them. So it's kind of internal property of these robots. It's not something which is external or imposed, as, for example, in active torque control robots. Okay, so therefore these advantages that we mentioned before, they are intrinsic properties of these robots. Okay, so and they don't lose them if, for example, control breaks. And one of the main research directions in the robotics community is to design and control the variable impedance or variable stiffness actuated robots. Variable impedance actuated joints, they have application in multiple fields and areas. For example, they're used in prosthetics, in surgical robots, in designing exoskeletons, okay, and in application related to interaction with the humans, in social robotics. So variable stiffness actuated robots is a subgroup, or it's one branch of the variable impedance actuated robot. Variable stiffness actuated robots, they also have the advantages of the variable impedance actuated robots. Specifically, these advantages are the following. So variable stiffness actuated robots, they consume less energy because they kind of consume energy at one cycle of the motion. Then they can store the energy in the nonlinear elastic elements, and then they can release that energy at the other cycles of the motion. Then they have variable stiffness actuated robots. They have increased maximum force and velocity capabilities. So due to the energy absorption abilities, and VSA robots, they can also easily absorb the external impacts or shock kind of impacts, okay, and again due to the presence of nonlinear elastic elements, and also these robots, they can protect, they are safe, they can protect the robot joints and the humans in case of collision. The variable impedance or variable stiffness actuated robots, they have the following kind of problems or difficulties associated with them. So firstly, design gets more complicated. Okay, so in other words, design of the variable stiffness or variable impedance actuated robots is more complicated due to the presence of additional nonlinear elastic and or nonlinear damping elements, and of the presence of the additional actuators. Okay. And also these robots, they have limited position accuracy, and they have reduced mechanical bandwidth compared to, for example, position control robots. Okay, and also they have more complex dynamics, and the parameter identification and the task planning of these robots is challenging. Okay. Finally, due to complicated design and nonlinear dynamics and constraints, the design and control of these robots becomes difficult, and intuitive tuning of these, for example, controllers cannot guarantee that we can utilize the variable stiffness or variable impedance actuated systems to their full potential, to their full extent. Our hypothesis is that we can exploit these systems to their full potential if we use optimal control methods to design and control them. A research group from Germany proposed the following control methodology to control variable stiffness or variable impedance actuated robots in 2013. Okay. They proposed to use optimal control problem formulation. So they take the system dynamics, and also they take the dynamics of the motor side, and they provide the dynamics to the optimal control problem formulation, and they specify the task, and then solve the optimal control problem and obtain the optimal control inputs, which they then feed to the system and get the desired behavior of the system. Okay? So this is the control methodology that they proposed. So control problem of variable stiffness actuated robots can be formulated as optimal control problem. Okay, so the purpose of the optimal control problem is to solve the following optimization problem. Okay, so here you have the cost function J, okay, which is called sometimes objective function. Okay, and then we have the system dynamics, here represented through the function f. Then we have constraints on the state x, and then we have bounds on the input u. Usually the cost function consists of two terms. One is called Lagrange term, another is called Meyer term, which is also describes kind of end term. By solving this optimal control problem, we can obtain the optimal control inputs to the system. Our approach to control variable impedance or variable stiffness actuated robots is the following. We propose to use the model operative controller to close the loop, and in this way to control the variable impedance actuated robots in closed loop manner. So in this case, the MPC controller takes the information about the current state of the system, okay, and then we provide to MPC also the solution from the optimal control problem as a reference. Then model predictive control, it compares the current state of the system with the reference state, and then it recomputes the optimal control inputs and feeds them to the system. In this way, we achieve the closed loop control. Model predictive control was first developed at the chemical industry, and it was firstly applied to the chemical processes. But due to the rapid advances in the microprocessor and electronics, now we can use model predictive control to the processes with fast dynamics, such as, for example, aerospace or mechatronics, automotive, and power electronics applications. Okay, in this work we used Akado toolkit, which is open source code to solve optimal control problems and to generate model predictive controller. And it has easy syntax in C++. The main advantage of the MPC is that it satisfies the system constraints, and it tries to get the system behavior as close as possible to its reference trajectory. Okay, usually for MPC we have to relax the constraints compared to OCP, optimal control problem, so that it can reject the disturbances. So this diagram describes how the model predictive control works. So MPC at every sampling time, it takes the information about the current state of the system. Then it has desired kind of trajectory of the system, or the desired set value for the system. Then it computes within the limited horizon duration, which is called prediction horizon. It computes the behavior of the system. Then, based on that, it calculates the optimal control inputs, which would try to bring the system as close as possible to the desired reference trajectory. So it computes these control inputs, usually for the control horizon duration, and then we just give the first control input, the first optimal control input to the system, and then we move to the next sampling time, where this process repeats. So essentially MPC, at every sampling time, it recomputes the optimal control inputs. So how do we describe the dynamics of the variable impedance or variable stiffness actuated robots? Usually for traditional rigid robots or position control robots, we just model the dynamics of the link side, while the dynamics of the actuator is usually lumped into the dynamics of the link side. So inertia and other properties of the actuators are lumped or incorporated into the properties of the link. While for variable stiffness or variable impedance actuated robots, we have to decouple, we have to consider them separately. So we have one equation which describes the dynamics of the link side. Then we have another set of equations which describe the dynamics of the actuators. Okay? So we have essentially these two different sets of equations, dynamical equations, which describes the respectively the dynamics of the link and actuator side. So in order to test efficacy of our proposed approach, we built the following two-link variable stiffness actuated robot. So the robot consists of the two links, 4 position-controlled motors, 4 nonlinear elastic elements, and 6 encoders. So in this robot, each actuator is connected to the links with the nonlinear elastic element, and the objective of the robot is to throw the tennis ball, which is attached at the end effector, to the farthest distance possible. So for that two-link variable stiffness robot, we formulated the following optimal control problem. So our main objective is to throw the ball to the maximum possible distance. So therefore, as our cost function, we have negative of the distance, d. So if we want to maximize distance, it's the same way as if we want to minimize the negative of the distance. But we also have these Lagrange terms here because we not only want to maximize the throwing distance, but we also want to minimize the energy consumption, and we also want to minimize the oscillations or motion of the motors. Okay, and therefore we have these Lagrange terms, and then we impose the constraints on the state and inputs, which actually reflect the physical constraints of the system. For example, we have limits on the motor torque, on the motor velocities. Okay, we have constraints on the extension of the nonlinear elastic elements, and so on. And then we formulate the optimal control problem for the duration of 4 seconds. And this OCP was solved in 16 minutes. Okay, with a sampling time of 10 or 20 milliseconds. Then we generated the model predictive controller, and for that we set the sampling time to 20 milliseconds, and we set the horizon time to 200 milliseconds. So we had 10 kind of sampling times within the horizon, prediction horizon, and then we slightly enlarged or slightly relaxed the constraint on the system. For example, we slightly increased the torque limit for the motors, and then we generated the MPC control using Akato C code. Okay, and we also provided as a reference to the MPC only link position and velocities. We didn't provide any actuator link and velocities as a reference. So on this slide, you can see the video of the experiments that we performed in the lab, and here on the slide you can see the actual distances that we achieved. So in the open loop scheme that we performed, in ideal case, in simulations we would achieve the throwing distance of 3.8 meters, while in closed loop would achieve distance almost close to that. Okay, only 3 centimeters less. Then in the experiments, in the actual experiments, in the nominal case, we obtained, in the open loop case, we obtained a throwing distance of 2 meters, while in the closed loop, we obtained the throwing distance of 3.2 meters, which is much larger than the open loop case. Then we performed additional experiments where we applied kind of external disturbances and where we changed the parameter of the system. And in both cases, you can see that the closed loop controller with MPC outperforms the open loop controller. Okay. But of course, we can apply the MPC to the control problem of variable impedance actuator robots if it satisfies the following condition. In other words, MPC should be able to solve the optimal control problem, finite horizon optimal control problem, within the sampling time. So in order to check if we satisfy this condition, we are showing the histogram of the computation time of the MPC, and as you can see, in all cases, the MPC solved the finite horizon optimal control problem in less than 12 milliseconds. And our sampling time was 20 milliseconds, so we were satisfying the time constraint. Then, in order to test the MPC approach, we did simulations where we applied the disturbances to the system, to the tooling system, and then we compared the performance of the open loop and closed loop systems. So here you can see the comparison of the open loop and closed loop system performances when external disturbance is applied. And as external disturbance, we used the external torque in simulations. So you can see that in most of the cases, MPC or closed loop controller, it compensates the effect of the external disturbances, and only in extreme cases its compensation effects fail. But in open loop case, we can see that at only specific values of the external disturbance, the system performance doesn't degrade, but in all other cases it degrades. Similarly, we perform simulations for the parameter variation case. In other words, we vary the parameters of the system so that the controller had different system values for the system parameters than the system in simulation. Okay, so we obtain the following plots. Okay, so here you can see the open loop and closed loop system performance when parameter variation of the system takes place. So you can again see that in closed loop controller, in most of the cases, it manages to compensate the effect of the different values of the system parameters, while the open loop controller, it cannot do that. The next task that we considered was related to the integrated optimal design and control of variable impedance actuated robots. Usually, the design and control problems of systems are considered as separate or decoupled problems. So, for example, designers, they design a system, and then after they design the system, they provide the system design to the control engineers, which then try to make the system controllable. So, but system design usually affects the controllability properties of the system, and the controllability properties of the system might in turn affect the design. Okay, so in other words, the control and design problem, they are coupled problems. They should be considered together. The traditional design methods, they doesn't allow to consider these two problems together, and therefore usually the design process is iterative process where engineers and scientists, they design the system in iterative manner, in iterative process, and they try to improve the system at each iterative stage. And but this process doesn't actually guarantee that at the end we get the optimal kind of design of the system. And so we propose to solve the optimal design and control problem together, as we propose to solve these problems using the optimal control problem methods, and which we call integrated optimal design and control problem. As a case study for this task, we considered again the two-link variable stiffness actuated robot. For this simulation, we considered the nonlinear elastic elements as quadratic springs. The constant is considered as design parameter. In order to find the optimal values for these design parameters or for the coefficients of the spring, the quadratic springs, we impose the following conditions. So we said that these parameters are states of the system, but the time differential is equal to 0, so they're constant, but the initial value is unspecified, so we just set the initial value within a certain interval, and then we formulated the following optimal control problem. So here our cost function is general cost function, but it also now contains the parameters to be optimized, P. Okay, and then we have system constraint, system dynamics. So for the as a case study for this task, we considered the two-link system, which was assumed to have quadratic springs, and we considered three different configurations. In the first configuration, all quadratic springs were the same; they were equal. So, in other words, the coefficients were the same. In the second configuration, the quadratic springs on one joint were the same, but they were different than the springs on the second joint. And in the third configuration, the quadratic springs on one side of the robot, for example, on the right side, were the same, but they were different than the quadratic springs on the left side. We got the following results. results for configuration 1 was the same as results for configuration 3. Therefore, here we just show the results for configuration 3. Optimal control problem gives the following optimal values for the spring parameters. So for the second configuration, the optimal values for the system parameters for the spring coefficients were 5, around 5 for the first link, and the maximum values for the second link. But for the third configuration, we got the optimal values of spring coefficients to be equal to maximum values within the allowed interval range. And in order to test whether these results are correct or not, we performed extensive simulations, and we obtained essentially the grid where we just were fixing the values of this of the spring coefficients, and we're obtaining the values of the cost function. You can see that this map actually proves that the solution which optimal control problem provided were indeed the optimal values. The next project that we considered was related to the reaction wheel integrated variable impedance actuator robot. Reaction wheels are commonly used in aerospace industry. For example, they're used in satellites to control and to stabilize the attitude, and they are also considered as additional torque and energy sources. So we propose to incorporate the reaction wheels into variable impedance actuator robots in order to increase the force and torque capabilities and to increase the bandwidth. And this is due to the fact that the reaction wheels, they store energy, kinetic energy, and then they can release that energy, and this is very helpful in performing explosive motions such as jumping, for example. And the reaction wheels are also have fast dynamics, and so they can assist variable impedance robots in precise position tracking and in, for example, disturbance rejection. As a test case for this task, we considered the single link variable stiffness actuated robot with the reaction wheel. It had the following constraints imposed on that. And then the controller had the following schematics. Okay, so the controller now had not only the motor side dynamics but also reaction wheel dynamics. And then the model project controller, it took this information about the motor side, about the reaction wheel, about the link side, and then it was computing the optimal control inputs at every sampling time. Here you can see the schematic diagram of the single link VSA robot with the reaction wheel, and here you can see the actual robot itself. Okay, so it has two position control motors with two nonlinear elastic elements, which were connected to the link. But then on the link itself, it had the reaction wheel, and then the ball attached at the end effector. So in order to test our control approach, we imposed the following task for the robot. So it had the task to throw the ball to the maximum possible distance. And we performed experiments for 3 different times, as you can see from the table. So robot motion was imposed as 1 second, at 1.5 seconds, and 2 seconds. Okay, and then here you can see on the table you can see the distances that we achieved. Okay, so you can see that reaction wheel with variable stiffness actuated robot together, the two systems combined together, they give the maximum distance at all cases, while the VSA only case and reaction wheel only case gives lower distances. For example, from this diagram, you can see that as time of motion of the robot is increased, the distance, the thrown distance of the ball also increases, but then it saturates. And so these results confirm that reaction wheels enhance the dynamics of the variable stiffness or variable damping or variable impedance actuated robots. On this slide, you can see the video of the experiments that we performed for this reaction wheel augmented variable stiffness actuated robot. The next task that we considered was related to time optimal control of variable impedance actuated robots. Often in industry, for example, it's necessary to perform a certain task in the shortest time possible or in the minimum time possible. The control sequence, the sequence of control inputs, which would minimize the time of motion, usually involves trial and error. So, and it's usually iterative process. But we propose to use optimal control problem to solve this time optimal control problem. Our approach, it takes into account the system dynamics and the constraints of the system, so that time optimal control problem is solved without violating the system constraints. Okay? And specifically, we propose two time optimal control problems. One is called minimum time for target performance, and another is called minimum time for maximum performance. For the minimum time for target performance optimal control problem, we have the following problem formulation. In this case, as a cost function or as an objective function, we have time of motion plus any function of the system states at the last moment of, for example, robot motion. Okay. Then we have the system dynamics. Then we have constraints on the system states and control inputs. Then we have a constraint on system performance, here specified by the letter phi. Performance criteria is imposed as the constraint of the system. So here you can see the formulation of the minimum time for maximum performance time optimal control problem. Okay. So actually this control problem consists of two sub-problems. In the first sub-problem, we want to maximize the system performance, okay, without constraint of the time of motion, okay. So in other words, we just maximize the system performance, and then in the next sub-problem, we want to achieve the performance which is maximum or which is slightly less than maximum, but which is close to maximum, but we want to minimize the time of motion. Okay, so here essentially minimum time for maximum performance is achieved by solving two suboptimal control problems. Okay, one in which firstly we maximize the performance, and then the other one where after that we minimize the time of motion while imposing the performance as constraint. We introduce the tolerance parameter delta, which takes into account errors of the computation, or sometimes maybe it takes into account the tolerance of the system. And this minimum time for maximum performance optimal control problem can be solved by time axis grid method, which can be applied for any time optimization problem, or it can be solved by bisection method. But this only is valid for the systems in which the performance is non-decreasing function. As a case study for this task, we used two different systems. The first system is the two-link variable stiffness robot, and as a second system, we used the single-link variable stiffness robot with the reaction wheel. On this slide, we present the results of a minimum time for target performance optimal control problem for the first system, in other words, for the two-link system. So, for example, on this table, we present the results of the optimal control problem solution, and for three different target performance values. As a performance function for our system, we use the ball thrown distance. And so you can see that for three different set values for ball thrown distance, we have the corresponding times. So T here gives the time of robot motion, and D gives us the time of flight of the ball after the system throws it and before it hits the ground. And then we have the combined times. So, and then on the lower side, you can see the diagram of the linkers of the two link trajectories and velocities and the corresponding velocities. For the same optimal control problem, minimum time for target performance, then we performed experiments. So for the two-link system, and experiments gave the following ball thrown distance values. So for the closed loop experiments, we achieved the distance of 1.9, 2.8 meters. So, but with open loop experiments, we achieved 0.8, 1.4, and 1.8 meters. So you can see that at each performance target value, the distance achieved by open loop experiments is less than the distance achieved by the closed loop experiments. So this result again confirmed that our proposed closed loop and latency control methodology gives better performance than open loop system. So here we present the results of simulations for minimum time for maximum performance optimal control problem for two systems, double link system and then a single link reaction wheel system. Minimum time for maximum performance optimal control problem was solved by two methods for each case study. One method is a time axis grid method, the other is bisection method. Here red dots represent the iterative steps of the bisection method, and then the blue columns they shows the results of the time axis grid method. And you can see that by using the time axis grid method we obtain the full map, but then the bisection method gives us the correct value of the solution, but with much shorter spent effort. On this slide, you can see the results of the bisection method applied to solve the minimum time for maximum performance and applied for the case study 1, in other words, for the double link system. With bold letters, we indicate the current, the solution of the current iterative step. You can see that within the 10 iterations, we get the optimal value for the minimum time. Here you can see the video of the experiments that we performed for the time optimal control problem. The next task that we considered was the energy optimal control of variable impedance actuated robots. In most of the applications in industry, it's desirable to reduce the energy consumption. Commonly, the reduction in energy consumption or energy efficiency is achieved by trial and error approach. And we propose to use optimal control problem to solve this energy optimal. So by using the optimal control problem, we ensure that system constraints are satisfied. And specifically, we propose to, we formulated and we propose to solve these three different energy optimal control problems. One is the maximum performance with limited energy, another is target performance with minimum energy, and the third one is maximum performance with minimum energy. So in order to calculate the energy consumption, we formulated the power equation, or the power consumed by the robot. And power in general consists of two terms. One is power consumed spent on resistance, okay, which is basically lost power, and another is the power spent on moving the links. So, and the total energy consumed is equal to integral of the time integral of the power. The first energy optimal control problem that we formulate is called maximum performance with limited energy, or MPLE. So in this optimal control problem, as a cost function, we have the performance function. Okay, so in other words, we want to maximize the performance of the system, but then we have the system dynamics, the constraints on states and inputs, and the constraint on the power, and we have the energy consumption of the robot as one of the constraints. So in other words, in this optimal control problem, we want to maximize the performance, but we have the limitation in energy consumption as one of the constraints. The second energy optimal control problem is called target performance with minimum energy, or TPME. So in this optimal control problem, we have as cost function the energy consumption, but then as a constraint we have the performance criteria. In other words, we set performance of the system as one of the constraints. So in this optimal control problem, we want to minimize the energy consumption, but keeping the system performance as one of the constraints. The third energy optimal control problem that we defined is called maximum performance with minimum energy. So or MPME. So in this optimal control problem, we actually have to solve two suboptimal control problems. In the first suboptimal control problem, we want to maximize the performance without any energy limitations. But then in the second suboptimal control problem, we want to get the maximum value of the performance that we obtained from the first suboptimal control problem, but we want to keep that performance criteria, but we want to minimize the energy. So in other words, in the second suboptimal control problem, we minimize the energy, but set the performance criteria close to or equal to the maximum performance, and we set this performance as a constraint. As a case study for this task, we considered a single link reaction wheel variable stiffness actuator robot, and this robot has 3 actuators, and therefore our total energy consumption of the robot consists of 3 energy terms, 1 energy for each actuator. And then we have the following system constraints, and the sampling time of simulations and experiments was 10 milliseconds. On this slide, you can see the results of maximum performance of limited energy simulations, or results of the optimal control problem, MPLE optimal control problem solution. So in order to obtain these results, we varied the time of robot motion, and we varied the amount of the allowed energy, or maximum allowed energy. And then we achieved the following values for the distance. And as you can see, as we increase the time and as we increase the maximum allowed energy, the distance increases, but then reaches the limit. You can see that the total energy spent has high values at the small times of robot motion. In other words, when we impose tight time constraints, then a robot consumes a lot of energy to achieve the desired strong distance, which is expected. On this slide, you can see the results of target performance with minimum energy optimal control problem solutions. And again, in order to obtain these graphs, we varied the robot motion execution time and set both around distance values. And again, you can see that if we increase the time and if we increase the set Boltzmann distance values, then the actual Boltzmann distance increases, but you can see that at very small robot execution times, the set values of the distance cannot be achieved. When we impose time constraint, then energy consumption is large because robot has to move rapidly in order to achieve the desired Boltzmann distance. Here we present the results of maximum performance with minimum energy optimal control problem solutions. On the table, you can see that for different tolerance criteria, epsilon values, we get different energy and certain distance values. And as you can see that introduction of the tolerance criteria is useful, because if you set this tolerance criteria to 0, which means that we want just to maximize the Boltzmann distance, then our energy consumption is large. But if we slightly reduce the tolerance criteria, then our Boltzmann distance reduces, but it also gives us a lot of energy savings. On this slide, you can see the results of experiments that we performed for open loop and closed loop systems, and for maximum performance limited energy optimal control problem. And here, in this case, we set the maximum energy allowed to 20 joules and time of robot motion execution 2.5 seconds. The next problem that we considered was related to successive linearization-based MPC. So for highly nonlinear dynamic systems, using nonlinear model predictive controller results in large sampling times because of the highly nonlinear dynamics. An MPC controller takes a lot of time to solve the finite horizon optimal controlling problem. So therefore we have to increase the sampling time. How can we reduce the sampling time? One way to reduce the sampling time is by linearizing the nonlinear model at the current state of the system, and then use the linearized model. But of course, when we linearize the model, then we introduce certain errors to the system, but because we use a linearized model, we can use smaller sampling times to solve MPC, and because we use smaller sampling times, it means we can negate the effect of errors introduced by linearization by using the smaller sampling times. So this slide shows the schematic of the control that we propose. So first we take the current state of the system, then we linearize the system, then we discretize the system, then we formulate the augmented model of the system, and then we give the augmented system to the quadratic problem formulation, and then we solve the quadratic programming problem and find the optimal control inputs, which then we feed to the variable stiffness actuator robot. As a case study for this task, we consider a single link variable stiffness actuator robot with the reaction wheel. And then we formulated successive linearization-based MPC for the task of tracking the reference trajectory for the link. Okay. And then we solved SLMPC using the QPOAssist open source quadratic programming solver. We set the horizon length to 200 milliseconds with a sampling time of 10 milliseconds. So in other words, we had 20 steps within the horizon duration. And then we did simulation experiments with the reference trajectory, which had a time duration of 16 seconds. So here you can see the results of the successive linearization-based MPC experiments. And so on the top figure, you can see the reference trajectory for the link, and then the actual trajectory that we achieved during the experiments. And then on the bottom, you can see the histogram of solving the quadratic programming problem by SLMPC and by NMPC. And you can see that in general, the average time of solving the optimal control problem by NMPC is around 2.1 millisecond, while the average time to solve the quadratic program problem by SLMPC is 1.25 milliseconds. So on average, SLMPC is almost twice faster than NMPC. But there are certain cases where SLMPC takes much longer than NMPC. On this slide, you can see the results of the experiments that we performed using NMPC and SLMPC controllers. You can see that both of them track the reference trajectory pretty well. But if we compute the root mean squared error for the reference trajectory, then NMPC performs slightly better than SLMPC, but this the difference is small. So let us summarize the advantages of using the nonlinear model predictive controller to control variable impedance actuator robots in closed-loop manner. So firstly, the NMPC is aware of system dynamics, and this might lead to better performance. The second advantage is that NMPC takes into account system constraints and bounds. So, and as a result, NMPC will not push the system outside of its capabilities or limits. NMPC also is independent of specific VI design, so the only things that we need to change when we apply NMPC to a different system is the system dynamics. NMPC is independent of the task, so just by changing the cost function, we can apply the NMPC controller for the different tasks. And NMPC is suboptimal, so at least it gives the suboptimal control inputs. And the NMPC actually ensures the optimal system trajectory. So NMPC tries as much as possible to make the system behave as we want it to behave. But of course, NMPC also has limitations. Okay? So the main limitation of NMPC is that it's limited by the computational power. So in other words, in order to implement NMPC to real systems, we have to ensure that computationally the NMPC can solve the optimal control problem within the sampling time. Then NMPC requires accurate model of the system. Another disadvantage is that NMPC requires the information about the current state of the system, so reliable sensors have to be used. And another disadvantage is that discontinuous nonlinearities cannot be incorporated into NMPC. As a future work, we have the following possible directions. One is soft robotics. So, in other words, a mechanical system with distributed variable impedance properties. They have increased capabilities. Of course, the design and control is difficult and non-trivial task. So we might apply an MPC to these systems. Then we have tensegrity systems, which have highly nonlinear dynamics and many constraints. And so the control and parameter identification are very challenging and difficult tasks. And then we might apply an MPC to distributed robotic systems, the distributed drone systems in an unknown environment, and so on and so on. So this concludes my presentation, and I would like to thank you for your attention, and if you have any questions, I am ready to answer them.